Um, Thanks, Razvan. As Razvan said, my name is Hamza, and they informed me that because I'm East European, it would be useful to say a few words about my path to DeepMind. So I come from Sarajevo, Bosnia, and I studied electrical engineering there, automatic control, and then I moved on to ETH in Zurich, where I did robotics and control, and then my professor at the time, who's a senior researcher at DeepMind, offered me a PhD position, and a few months later he retracted it because he decided to join DeepMind. But instead he offered to give me, to write a letter of recommendation, and then the whole process started, and in the end I decided to join DeepMind instead of doing a PhD, and luckily there's a PhD program at DeepMind, which I started last year. So I kind of managed to get best of both worlds. So yeah, today I'm going to be talking about deep reinforcement learning. The presentation is based off of slides made by Dojnaš, so she did most of the hard work, and I guess I'm the foolish one to jump on doing this presentation with 1 day notice. I've modified the slides a little bit to add some of the, I guess, Balkans sense of humor to the talk. But yeah, there might be a few hiccups, so please bear with me. And yeah, hopefully you'll get to learn a bit about deep reinforcement learning, and if not, maybe hopefully laugh a little bit. So the rough structure of the talk, we're going to first introduce reinforcement learning, then we're going to talk about the main components that comprise an RL agent, and then we're going to talk about some of the main concepts in RL, such as episodic and continuing reinforcement learning, value functions, estimation, and function approximation. We're going to talk about the difference between on-policy and off-policy control, and other topics such as exploration versus exploitation dilemma. And then we're going to go through some of the representative RL algorithms. There's also a tutorial on RL later on, which kind of ties this together quite nicely. So let's begin. Reinforcement learning, as opposed to standard supervised learning, deals with learning from interaction. So we generally assume that there's an agent that operates within an environment, and it gets a signal. For example, in the animal learning theory, that could be like an agent could be a mouse and have a little task and receive food or shock as the reward. But conceptually, an agent could be a program which receives some numerical values that go up and down, and the aim is to sort of optimize the behavior to maximize this reward during the whole lifetime of the agent. So the agent receives some perceptions and rewards, and it acts on the environment. I guess there's like a philosophical debate, often whether reinforcement learning is more natural than supervised learning. Like, I guess animals and kids learn through incentives. But when I first learned about reinforcement learning, there was actually no doubt. Like growing up as a East European boy, I guess it was way more natural to learn through reinforcement. I guess often negative, let's say, sticks, brooms, and occasional slipper, I guess. So yeah, it's learning through trial and error, and reward or the penalty can be delayed, which complicates the task. So often you need to, like, there's a whole field within reinforcement learning called credit assignment, where in a long lifespan, we need to figure out which actions actually led to the outcome, to the reward. So as a motivating example, we can look at AlphaGo and AlphaZero, which are tasked at learning how to play the game of Go, which is this ancient Chinese game, quite complex space of actions and possibilities. So the perception here is the state of the board, so the position of these black and white stones, and the actions are a set of legal moves. So the set of actions changes over time because there's less legal moves that the agent can play. And the reward is can be plus or minus 1 depending on the outcome of the game. So in this case, there are two important components for the agent that we're going to be talking a lot about in this talk, which are the policy network, which is essentially a function, or usually like a deep network that provides a probability density, probability mass function of all possible actions given the state of the board, and then the value network, which estimates sort of the goodness of the position, which estimates the likelihood in this case of winning the game or not. So because it's a complex game, it takes a lot of time and a lot of actions. To find the correlations between good actions and good outcomes, we need a lot of data. So Go is quite interesting because it allows self-play, essentially. It allows an agent to play against itself to generate large quantities of data, and through that kind of figure out which actions are good or bad. In these complex cases, why RL is interesting is because as some of you might have seen if you watched the AlphaGo documentary, you've seen this like famous move which blew the minds of the whole Go community, which essentially through self-play the agent was able to go beyond the human capabilities and invent new ways of approaching the game. So some of the historic RL successes. In the 1950s, 1995, there was the first proof of concept of TD learning, which was used to train an agent to play backgammon. And then it's nice that Doina put the helicopter autopilots, because this was actually the first application of reinforcement learning that I've seen that got me into RL by Andrew Ang. And then there's like, RL is kind of ubiquitous across the board, like it's been used for marketing strategies, for things like IBM Watson's Jeopardy, and then I guess more recently, which we're going to be mentioning here, like the Google DeepMind, Atari games, and so on. So, wow, okay. Yeah, so the slides kind of showcases some of recent RL successes that Doina particularly likes. So the first one is the autonomous navigation of balloons using reinforcement learning. So balloons are moving around in stratosphere, and there are different currents at different levels, different heights, and the control objective is to keep the balloon in a specified place, and the balloon can move up and down and kind of chase currents to stabilize it in place. And another approach, another example of this is the control of a tokamak for nuclear fusion. So a work that has a high potential real-world impact for clean energy and so on. I also added this slide by a famous slide, some of you might have seen it a few years ago, from a famous senior researcher, Jan LeCun at Meta, where he compares RL, or like deems it as a cherry on top. Because RL is interesting. It has less signal. The reward signal is usually quite sparse compared to other signals in the environment, like vision and language and all the data. Jan LeCun often talks about this and says that like it's actually the bulk of the learning that we can do is through self-supervision, through like finding interesting ways of using all the data that we can, and then using the supervised learning where we have labels, and then get the final bit of the performance through RL. But often this cherry on top is what really makes the difference. So we've seen in 2013, when the first largest networks at the time, the convolutional networks like AlexNet, were coupled with RL, we got deep-Q learning, which kind of propelled DeepMind to the forefront of AI. And we're going to talk about this later in the slides. And then also in 2021, the combination of transformers, large models, and RL, we got the first RLHF instruct GPT example, which then evolved into ChatGPT and also propelled OpenAI. Yeah, we don't want to talk about this. No, I'm just kidding. Like there's going to be future talks about RLHF. We're not going to be touching this in the in this presentation. So some of the key features of RL are basically that like the learner is essentially not told what to do. It has to figure it out through trial and error. The environment is generally stochastic by assumption, though of course it works with deterministic environments. As I mentioned earlier, rewards may be delayed, which complicates the problem and puts the credit assignment question forward. And then there's what we're also going to be mentioning is there's a need for balancing sort of exploration and exploitation within the environment. So sort of figuring out what's possible to do versus choosing the best things to do within the environment. And reinforcement learning kind of ties itself well, connects itself well with many other areas, such as computer science, neuroscience, psychology, economics, and so on. So it's not only useful to solve problems in these fields, it's also useful to formulate the problems through the lens of RL, through the way of sort of actions that can be taken and the outcomes and so on. One second. The general computational framework that we use when we talk about RL is like, as I mentioned earlier, we assume an agent that interacts with the environment, and through this interaction, the agent receives a state from the environment, which it then uses to select an action, and then gets a reward and transitions into a new state. I mean, the agent receives a perception signal, which is usually the sort of partially observable part of the environment, so it doesn't receive the full state. And the goal is that we're tasked with is to figure out a policy that is a function that maps from these states to actions that hopefully maximize the future sum of rewards. And then when we talk about the interface, we assume generally like a discrete time, an agent acting in time steps, observes a state, ST from the set of states, and selects an action, AT, and then receives a reward, RT plus 1, after the fact, and transitions into a new state, ST plus 1. Now, comparing RL, as I mentioned, the agent is not really directly shown what to do. It needs to figure out what to do on its own through trial and error. This contrasts with behavior cloning, where we have some data on states, observations and actions, and the agent essentially just optimizes an error minimizing loss to imitate the actions that are found in the data set. While the difference with reinforcement learning is that the agent, the outputs that the agent produces there's quite a bit of a distance between the output and the actual objective. In behavior cloning, the output is the action, the objective is the action. In reinforcement learning, the output is an action, but the objective is a reward. So there's kind of like a bit of a indirect connection, and that's what makes RL complicated, but also quite interesting. And so, yeah, as we mentioned, the goal is to get the policy, which is the probability over actions given states. The policy can be deterministic, but we generally assume that it's a distribution. Yeah, I guess we can, and yeah, and through interaction we get these transitions like state, action, reward, next state, tuples, and yeah, as I said, the goal, multiple times the goal is to optimize the reward. And to optimize the reward, we look at the quantity called the return. So assuming that we have some interaction within the environment and we have a set of rewards, we want to essentially optimize the sum of rewards. So there's multiple cases that we can optimize. There's like the total sum of rewards, the average reward, and the mean reward, but generally we usually just focus on the total sum of rewards. So for episodic tasks where there's a clear start, so episodic tasks are tasks where we can kind of bound an episode, where we can say there's a concrete start and end of the interaction. So the interaction is broken down naturally in episodes. We generally just use the sum of all the rewards within the episode until the terminal state. So as an example, like a canonical example in this space is the mountain car. So the goal here is to get to the top of the hill as quickly as possible, but just accelerating towards the top is not possible. So the agent kind of needs to use momentum and swing back and forth a little bit to figure out the way and reach the top. And now the question here, so like the episode ends once the agent reaches the top of the hill, and we can think about ways of defining the rewards in this setup. So a common way would be to receive a negative reward throughout the whole time until -1 reward until the agent reaches the top of the hill. So this essentially, if you think about it, it incentivizes the agent to move to the top of the hill as quickly as possible, because the more time it spends moving around, the more negative reward it gets. Now, compared to episodic tasks where there's a clear delineation between beginning and the end of the task, continuing tasks don't really have this property. So either the episodes could be of unknown length or indefinite length. And in this case, we generally don't just maximize the sum of rewards, but we use discounting. So we introduce parameter gamma, which provides a trade-off between immediate rewards, how much we value immediate rewards versus future rewards. This is useful not just for essentially for providing this preference of whether we value immediate rewards more than rewards later in the interaction, but it's also generally important for numerical stability. And there's a lot of research as well. If you've seen, for example, things like the marshmallow challenge, or like in psychology, there's also indications that humans have some sort of discounting, and obviously we value rewards that are near to us than rewards in the future. So yeah, this is one of the things that's also kind of provides numerical stability, allows us to encode our preferences, and also aligns with research in psychology and neuroscience. So here, you will see this example in the tutorial later on, but one canonical example of continuing tasks is pole balancing, where the goal is to keep the pole vertical for as long as possible. So we can, and within the bounds of the space where it can move. So we can formulate this problem as an episodic task, where the episode ends once the pole falls down or it moves beyond the boundaries. And in this case, we can say the reward is positive for the duration of balancing, and then the final return is essentially the number of steps that the agent has lived within the environment. Or we can formulate this as a continuing task, where we essentially don't know when it's going to end, and we just say that reward is going to be -1 upon failure. So this gives us the return of minus gamma to the power of k. So this return sort of decreases as the agent, it increases as the agent spends more time in the environment. So this example showcases two ways of specifying the reward for the same task. And it also highlights that this is usually, specifying these rewards is something that it can be given to us by the environment, but it's also something that we choose based on the task at hand. And there are certain ways of specifying the reward that are better than others. So if you look at the first example, the reward, we say that the reward here is, in the first case, in the episodic task, the reward here is quite dense. So we get a reward at every step. While in the continuing task, the reward is sparse. And it's often the formulation with sparser rewards is higher variance, and it's more difficult for our agents to learn. So that's also a consideration when we design and formulate RL problems. Before we get into value functions, are there any questions at this point? Yes? So the question is whether in the continuing task we sort of continuously, if I got it correctly, if we continuously update the functions that we're learning, or whether we do something else, whether we do bootstrapping or stuff like that. So this is something that we're going to discuss go into detail further on. So yeah, if something is unclear, you can ask again. So, okay. Now that we've defined this return value, we want to make use of it, and to use it, we essentially define another quantity, which or set of quantities, which we call value functions. And value functions are functions that try to estimate the return from the current state until the end of the episode. And there are commonly 4 types of value functions. So, or 2 types broadly, like state values and action values. And we either we have these 4 theoretical objects, which depend whether we're using prediction, so whether the functions are conditioned on the actual policy, or whether we're doing control, whether we're actually looking for the optimal value function, the value function that maximizes the reward. So what this means is that we can have a policy that's maybe suboptimal, but it will have a certain value, and through value functions we can compare essentially different policies, and we can use that, as we'll see moving on, we can use that to compare values and to optimize the policies, to find policies that have better values. Now, the difference between state values and action values is that state values sort of average out across all the possible actions, while action values include the next action taken. So as you can see here, state value functions are just a function of the state, so they kind of compute an expectation over all possible actions, and action value functions ask the question what's the value if we're in this state, but we also take this action. So this kind of helps us look at all the different actions and choose the best one. So the more formally, a value of a state under a certain policy is defined via this equation. So it's the expectation of the future return given the state that we're currently in. And the value of an action is also, we're considering that we're taking an action in the state, and we look at the future discounted return. So to ground this a little bit, we can look at the grid world example. So we assume an agent in the grid world, and there's like some rewards if an agent jumps from state A to A prime or B to B prime, and the agent can move around in the grid, and if it goes off the grid, it receives a negative reward. And so we can look at a random policy in this case, so the agent can just move around randomly, and we can evaluate this. As we mentioned before, we can compute the values at different states, and we can see that, for example, in this state, because the agent can jump to state A prime and receive a high reward, the value is high compared to other states where to get to the high reward, it needs to move around and risks going off the grid. And as you can see, these values kind of give us some sort of a goodness of the particular state and allow us to do some sort of investigation just by eye. Even with this random policy, we can get a sense of, without knowing the grid layout, we can get a sense of where the good rewards are and so on. And so we've talked about value functions, but now how do we train these value functions? So one simple way to do it is what is called Monte Carlo estimation. Monte Carlo is generally essentially sampling from the distribution. So what this means in the case of RL is that we can compute an unroll. We can just run the policy until the end, and then we can compute the return. We can then, to compute the value, we can just do this sort of simple update step, which can be shown that essentially in expectation, as we do this over and over again, we will converge to the actual value of the state under a policy. And of course, instead of doing this simple update step that we mentioned earlier, we can use this as the target for learning, and we can use function approximation. So in this case, we can, by function approximation, I mean we can parameterize the function to estimate the values. And the objective in this case is the mean squared value error, which is weighted by this quantity mu of s, which you can think of as the total amount of time spent in the state S. So this just comes from the expectation of the policy. Just to ground this function approximation a little bit more, this is an example where we have 1,000 states with a random walk. There's a random walk that starts at a state 500, and then it moves left or right, jumps between up to 100 states, either left or right, and terminates with -1 if it goes all the way to the left, or +1 if it goes to the right. So function approximation, it's an approximation essentially. So it means that we don't look at the states as a continuum, but like we lose some of the information. So to incorporate that, what we're going to do is we're going to bin the states here, and we're going to do it such that we have 10 state groups, and we're going to assume that we're going to compute the average of the value within those states. And once we do, in this case, Monte Carlo estimation, we essentially run this random process over and over again. What we get is something like this step function. So the true value in this case, depending on the state distribution, but in this case, it's just going to be a line with slope of 45 degrees. But because we've introduced this approximation, we're getting approximation errors. So we get this kind of coarseness in our function. So now, yeah, okay, maybe this is also a good time for questions, if there are any. Okay, cool. So if you've read RL papers, usually in the problem statement, there's always a definition of something called the Markov decision process. Usually we assume, in reinforcement learning tasks, we assume this Markov property, which is essentially the memorylessness of a system. So it means that if you look at the probability distribution, this is for some sort of autoregressive modeling, if we condition on the whole past, the whole history, we don't actually conditioned on the last state, everything else is essentially independent, so it's not important. So we can write this probability of the next state as just conditioned on the last state. So it means that this idea of no memory, it means that all the information that is contained is that we need to worry about is contained in the last state. So this is a common assumption that then, together with what we've discussed, with the states, actions, transition functions, discount, and so on, this defines the Markov decision process. So it's a process that we've described plus this Markovian property. This Markovian property is important because coupled with another principle called the optimality principle, which a simple intuition is that when you look at shortest path problems, so for example, if we know that the shortest path from Novi Sad to Niš goes through Belgrade, then we also know that Belgrade to Niš, the same road, is going to be optimal for that path as well. So what this allows us to do is it allows us to essentially work recursively, work backwards. And it allows us to say that, like, to look for optimal paths back from Niš, find the best paths from Belgrade, and now we can then look at the optimal paths from Belgrade to Novi Sad and maybe look through the optimal paths through other cities, and in essence we'll be doing this sort of recursively. We're essentially guaranteed to reach the optimal path, and this kind of ties in well with the once we have these optimal state and value function, state value and action value functions, we can then use them. So one way of using them is, if you're familiar with dynamic programming, this is exactly what underpins dynamic programming, where we can recursively work backwards. And in this case, if we have this Markovian property and we have the optimality, then optimality of value functions, for example, in this case, then we can easily get the optimal policy, just as I mentioned earlier, just by comparing the values at neighboring, here in this example, back to the grid world, by comparing the values. So we can see here that, for example, the value is 24.4 and here is 22. So it means that from this state, the optimal pad is looking at the neighboring cell with the highest value, which is this. So just by reading this value table, we can infer the policy, the optimal policy directly. So if you're familiar with dynamic programming, often there we have two steps. one called policy evaluation, where we compute the value of a certain policy, and then we do some update to improve the policy based on the computed value and so on. So the idea here is the same. So once we have these value functions, once we've estimated them, we can then use them to get the optimal policy. And this is essentially called sort of comes from this Bellman equation, where you can see the recursiveness shows up here, where G of t can be written as the next reward plus the future G of t. And this is this recursive idea where, again, if we've computed the future optimal value, we can use it to infer the optimal value of the current state. And so, yeah, as I mentioned, in dynamic programming, like we're going to contrast here, like we're looking at a specific state and all the transitions from this state. So the black dots are actions and the white dots are states. So in dynamic programming, we're going to bootstrap. Essentially, we're going to look at all the transitions and compute the value as a reward, as the expectation over the sum of reward and the future transition. But now contrasting that to Monte Carlo, as we mentioned, we do the value estimation by doing sort of a depth-first search and doing it over and over again to get the expectation. But another approach for estimating values is what is called the TD learning, temporal difference learning. So here, it's kind of a mix between the two. So we don't look at all of the transitions, as in dynamic programming. We look at a specific path, so we have this kind of iterative procedure, but we still do bootstrapping. So we still cut the trace short, and as in dynamic programming, we bootstrap from the future value. And this is essentially, so temporal difference learning is a really cool idea. It's one of these really unique ideas which AI researchers came up with, I think, in the 80s or 90s. And it's really unique because it then got picked up by neuroscience research, and they found that TD learning explains quite well how dopamine neurons work. Like they essentially bootstrap and anticipate the value in the next state. So this TD learning essentially is used for, as I mentioned, for evaluation, and compared to the Monte Carlo method, where the target is the actual full return, here we have some sort of an estimate of the return, which hinges on the Markovian property. And then here, this slide just kind of shows different ways of learning now that we have these kinds of these targets and different assumptions. So it kind of we just want to showcase with this slide essentially that we can build these estimates and have different update rules that have different properties, essentially different numerical properties for learning. And they depend on the agent behavior, but also these future estimates, so this bootstrapping idea. And a good example to showcase the difference between Monte Carlo and TD learning is this example where we essentially assume a Markovian property, and we have a set of transitions. We have 8 transitions in total, so we have from A, we receive a reward 0 and transition to state B, and then we receive a reward 0. Then we have 6 transitions where we go from B to, where we go from B and receive a reward 1, and then finally we go from B and receive a reward of 0. So now, if we look at Monte Carlo estimate, for the value of B, it's relatively straightforward. We can just compute the average of these rewards. So we know that we have 6 ones and 2 zeros, so the value is essentially 6 over 8, which is 0.75. But if we look at, but the question is, how do we get the value of A? So in Monte Carlo, we look at the transition starting from A, and we would conclude here, like our estimate would say that the value at A is 0, because we just have a single episode with total 0 reward. But if we look at TD learning, we're essentially bootstrapping, and we say, okay, we have a transition from A to B, so the value is not just this single episode, but it's actually bootstrapped. So it's the reward from transitioning to B plus the value of B. So in Monte Carlo, we would get 0, but in TD learning, we would get the estimate being 0.75. So this just shows that once we incorporate this Markov property, it encodes something about some assumption within the environment. And this assumption can speed up learning, but it also provides a certain bias into the system. So essentially, like with Monte Carlo, it's gradient-based, and we're guaranteed with enough time to converge to the local optimum. But with temporal difference learning, we can get there faster, but we might have to do there's no free lunch usually. So that means that like we might get there faster, but we might introduce some bias in the system. So we might, essentially, we say that like Monte Carlo is 0 bias, high variance, while TD is low variance, but potentially high bias. And we can see this here in the example that we showed earlier, where if we approximate and we use TD learning, we will potentially get some drift, which is usually at the edges of the state. So this is the bias at hand because of this bootstrapping, because we are estimating the value based on the value estimate. So if we have some error, this error will keep propagating unless we do something smart about it. And what I've talked about so far in TD learning was TD0. So this means that we just bootstrap after a single transition, but we can interpolate between the two. There's a lever that we can pull, which is called TDN, or n-step returns. So we can trade off between Monte Carlo and standard TD learning by doing multiple steps before bootstrapping. And then if we say that we want to do infinite steps or run the learning on the transitions until the episode end, we essentially get Monte Carlo. So this is a way to trade off between bias and variance, and this is just kind of formalized in this slide, where Monte Carlo does the full unroll until the end of the episode, and then TD0 does a single transition, and then TDN, we can have as many as we want. And in this example, we can just see how changing ends gives us a different estimation error. So, and it really is a trade-off. So it's not really that like higher ends always give better results or lower ends give worse results, but something in between is, depending often on the environment and the stochasticity of the environment itself, is what gives us the best results. And this kind of ties in well with this, looking at all these different possibilities, we can build a unifying view of value estimation. So at the bottom right corner is the exhaustive search, which is essentially saying we're going to run all the transitions infinite times, which is not something we generally do in practice. At the top, we have temporal difference learning, and dynamic programming, which assume an implicit model, which assume a Markovian property. And then Monte Carlo, which is unbiased, it makes no assumptions of the sort, but as I mentioned, has higher variance. And then we can sort of move in between and choose the method adequate to our problem. Okay, so this was about learning values, and hopefully it answers your question. Depending on the task at hand, we can choose how we bootstrap. And then we can, once we have the value estimates, then the question is, how do we use them for control? How do we use them to select the policies? So in general, as we've seen in the previous example in the grid world, we can, in these simple cases, we can just look at the values of the neighboring states, and through that we can pick the actions that lead us to the states of the highest value. But once we introduce function approximation, once we get into more complicated state and action spaces, this becomes infeasible. So the goal of control is to provide ways to use these values as a learning signal to improve the policy. So essentially, we want to move the policy towards a greedy policy. And a greedy policy is essentially the policy that exploits, that wants to give us the highest reward. But in general, as I mentioned earlier, we want to balance this out with exploration. So another assumption for these algorithms generally to converge is something that's called ergodicity, which means that we want to visit ideally we want to cover the whole state space. We want to see the whole world to better know what the optimal thing to do in the world is. And to do that, one simple idea is to use this epsilon greedy exploration strategy, where we say we're going to take an action, optimal action, let's say if epsilon is 5%, we say we're going to take a random action 5% of the time, but then we're going to take the optimal action 95% of the time. And this, through time, sort of guarantees, under certain assumptions, but like usually guarantees that like we're going to explore the whole state space and we're going to converge to the optimal solution. And based on this, yeah, so there are different algorithms for learning this, for updating parameters in the case of function approximation. So like you will see mention of, like we mentioned Monte Carlo, you will see mention of SARSA, expected SARSA, and dynamic programming. So these are all on policy algorithms, and what changes, like the learning rule formulation is the same in all of those. It's just the estimate that changes. And for exploration, these are two graphs that show how the performance of the agent changes depending on the epsilon, the exploration. So you can see here when epsilon is 0, when it's greedy, the agent won't explore enough of the state space to be able to reach the optimal value. So it will get stuck in some local optima. And now, once we sweep and once we change the epsilon, we change the performance of the agent. And in this case, if we run the agent for long enough, we're going to see that the red curve overtakes the black curve and the performance gets better in the end, just because of the fact that we're doing less random actions. But the cost of that is that like learning is a bit slower because we're doing less of exploration and more of exploitation. So in general, to get the best of both worlds, we usually anneal epsilon. So we start with a high value. We let our agent explore a lot while it's young, let it make mistakes and see the world, and then as it's getting older and older, it starts doing the stuff it's used to and profit from the things it likes and has seen. And the second graph, it just shows basically like the probability of the optimal action given the epsilon. So it kind of it corresponds to like what you would expect. Oh, another transition, and this is just like before we've seen how by changing. Or actually, maybe I've skipped that slide. So before we've seen how changing n gives us different values of different performance for value estimation. Here we see just that the same holds for control as well. So if we do n-step return, n-step SARSA in the mountain car example, we not only see better learning of the value function, but we also see improved learning for the policy as well. Okay, are there any questions at this point? Yes. So the question is whether the order of episodes matter when we talk about Monte Carlo and TD. So in general, it does matter, and you can take a look at, for example, TD lambda algorithms. So the order matters. Like if we learn about one state because we're bootstrapping, then we will use what we've learned. So essentially as a signal, as a guiding signal. So if we've changed the order of things how we've learned, it will make a difference for TD. For Monte Carlo, in general, it shouldn't be as dependent as TD learning. So TD lambda is a way to try to address this limitation in TD learning, or to minimize it, because it keeps track of certain traces and the past, but it still doesn't prevent fully this difference in ordering that we get. I don't know. We can discuss this later. There was another. Yes.
Can you scroll back, please, to where you showed us an example of an optimal policy with the grid one? Because there was like on the fourth box from left to right on the top row here. Why the fourth box on the top row has like any direction?
I think this just means that this is some sort of
Shouldn't this be the optimal policy? The third, the C one.
So you mean this one?
Yeah, exactly. Why is it direction? Shouldn't it be?
I think this just signals that these are terminal states. So once we reach those, then we essentially, any action you take jumps to B, or so you see here, like once you reach B, it takes you to B prime, and you get so this jump happens no matter what action you take. I think it's just a little nit within the environment that I haven't explained. So the action that you take here doesn't really matter. It's not really, maybe terminal state is not the best word, but essentially the jump happens as soon as you reach B, if I understand the environment correctly.
Those jumps are embedded in the environment, right?
Yes, yes. Yep.
So during the exploration constant, when you talk about the exploration constant, so does the exploration, where you explore matters as well as exploration constant? As I understand, like if you talk about exploration, that means while we're exploring, it will simply be a uniform distribution. So my question would be, in case of like a large state space, and uniform policy might not always work. So can there be some ways there so that we could like pick where to explore?
Yeah, so I mean, at the end of the talk, there's a slide on open problems, and exploration is still one of the big open problems. In grid world, in general, we can see that epsilon works quite well, but in complicated tasks, we need something with complicated state spaces. It requires a lot more thought. And we also use some naive methods like just entropy regularization to make all the actions probable, but that's just patching a bug, not really addressing the problem properly. Okay, I'm gonna move on. How are we on time? Okay. So we talked about on-policy learning, which is when we learn about the values and try to optimize the policy that we're currently taking. So we've mentioned Monte Carlo and TD learning and so on. In that context, SARSA and so on. But now I'm going to talk about Q-learning. And Q-learning essentially assumes that when we bootstrap, we are not taking the action that our policy says, but we're taking the maximum action, the action that gives us the maximum value. So this essentially, what this allows us to do, it allows us to get a bunch of different transitions in the environment. They could come from a random policy. And then we can learn the optimal policy or the optimal value function from any transitions. So that's quite powerful because it allows us to have this difference and to learn on data that is unstructured and maybe comes from like an unknown source. The trade-off is often that these methods are a bit less sample efficient, so they require more data to learn, but they have much more expressivity in the way of like tackling different problems, and these are methods that are generally used for things like offline reinforcement learning and so on, where we don't even have an online policy to collect the data from. But Q-learning essentially generally is like very sound if we don't use function approximation, but when we start doing function approximation, we start getting a lot of issues because of the maximum operator, among other things. But we mentioned earlier how TD methods suffer from bias because we're making an assumption. We're doing this bootstrapping. So if our prediction of the future is bad, we're going to be propagating this error. And in Q-learning, it's even more. It's even a bigger problem because we're not using the estimate. We're using the sort of the optimistic view. We look at the maximum value. So this just makes the errors propagate even worse, essentially. So this was a big problem for that. Moves the theoretical understanding, the soundness of Q-learning, and makes it difficult to apply in practice. And this is one of the crucial things that DeepQ network, DQN work, tackled. So the idea of DeepQ learning is to learn to play video games from raw pixels, essentially Atari video games, just by interacting with the environment. And the goal here is to learn the Q function, and we have a deep network which looks at the pixels. It encodes the Markov property, so this is one frame that shows that. So instead of, as we mentioned, we want to have the state that maintains the useful history. So instead of just looking at the last frame of the game, we look at n last frames. In DQN, that's generally been used 4 frames. For Atari, seems to be enough. We had this deep neural network, and to actually stabilize learning, the key components were, like the intuition between key components that made DQN work were to try to make Q learning as close to supervised learning as possible. And to do that, one important piece was target networks. So we want to not change the function that we're bootstrapping from as often, just to not propagate this optimistic error as much. So we freeze the network for some number of steps, and this makes the problem closer to to supervised learning. So you will sometimes see Q-learning referred to as a semi-gradient method, so not a true gradient, just because of this bootstrapping property, because we're trying to pass the gradient through something that's also a function of the parameters, but we ignore this contribution to the gradient. So this is one thing that like target networks help stabilize. And the other thing is the experience replay. So in TD learning, there's usually, if we get, so what we mentioned earlier about how the order of updates matters. And it matters especially if we feed the data in the same order as it's generated, we get a lot of correlation, and the correlation further breaks. Often in supervised learning, you have these IID assumptions. So experience replay was crucial for this. So instead of piping the data generated directly into the learner, what we do is we write the data into a large buffer and then sample uniformly from that buffer, just to break any correlations and to, in expectation, basically break this ordering, the issues that ordering causes. And then the success of deep Q learning was not just learning to play a single Atari game, but like then with further extensions, getting a single network that plays any game and learns to understand any of the games better than all the previous algorithms, and in a lot of cases at human level. And this is just an example of a trained agent playing Breakout. And DQN essentially started a revolution in reinforcement learning. It was the first large-scale example of using deep, large networks and function approximation with reinforcement learning. And since then, there's been loads of extensions to handle different problems, usually revolving around this overestimation of the Q networks, like the double Q learning and dueling networks. And there's been other works that make incremental improvements on this. One important idea is prioritized experience replay. So we mentioned that there's this assumption of IID-ness, and that this gets broken if we don't use a prioritized replay, but we can move this a step further, and we can learn on informative transitions. So we can prioritize not uniformly, but we can sample not uniformly, but prioritized, so using TD error and prioritizing based on proportion of TD error. So what this gives us is essentially, it lets the agent focus on transitions that have a large error, so transitions that it doesn't understand well enough. And this is actually a key idea of a paper that I submitted 2 weeks ago, which does the same thing, but for supervised learning, where we have an error, and instead of learning on the IID data, so like randomly sampled data, we find smart ways of prioritizing data based on a certain error, what we call a learnability score. And just by using that, by taking this idea from the reinforcement learning literature and applying it to supervised learning, we were able to get 10 times speed up training large models for vision and language on supervised learning. And then there's a whole suite of different improvements that I mentioned. And then there's this rainbow agent, which shows, it's an interesting paper which compares all these different improvements and puts them all into a single agent and essentially doubles the performance of human, average human performance. And so far, basically what we've mentioned are these action value methods, which Q-learning belongs to. So methods where we look at the action value function, and we learn the value function, and then from the value function, we select actions that maximize it. So usually, like we choose the, we optimize the policy by choosing the maximum actions. But it's not always the best idea to take this indirect route, to first learn the values, estimate the values, and then train the policy that maximizes that. We can actually just directly learn the policy under certain assumptions. And this is where these actor-critic methods that we're going to mention fit, where like they essentially use the best of both worlds. So to understand this policy gradient, and I would encourage you, if you're math savvy, these are very interesting papers from Rich Sutton on stochastic policy gradient, deterministic policy gradient, and then from Williams reinforce. They're like really nice and show like some interesting tricks in probability and how we can derive these interesting updates from just reward signals. So you will often see the derivative of the log of the probability, and this is just because of this important sampling coefficient, because there's this relation here that the derivative of pi over pi is the derivative of the log of pi. And if we look at the policy gradient theorem, it just says that so this is the proof within one of Rich Sutton's papers, where if we differentiate through the value, if we want to find the maximum improvement of the value, this derivative doesn't depend on the state visitation. So this was what we called mu in the beginning, and this is the action value function, but the derivative just pertains to the actual policy that we make stochastic. So anyway, you will see this a little bit in the tutorial later today, and this is a part of the derivation of a reinforced algorithm that comes from this, and you see this derivative of log pi that emerges. But the takeaway here is that the derivative, the maximum improvement, is just essentially the product of our return and the derivative over the logarithm of the policy, which is a super clean result. And there's an expectation over policy, which just means that when we sample multiple interactions, we can just use this product as the update rule, and in expectation, we should converge to some local optima. And now, to motivate actor-critic methods, which you might have heard of before, we go via the route of introducing a baseline here. So there's this equivalence that this line and this line are the same value, because once we add a value, like once we add or subtract a value to the action value function here, if this value is only a function of the state but not an action, then it can go before this summation here, and then it essentially just cancels out. It sums to 0. So we can add arbitrary functions of the state, and we won't change the result in this case. But what this helps is it helps with reducing variance once we do sample-based estimation. And there are smart ways of learning this, and that's exactly what actor-critic methods do. They use for the baseline, for this value here, they use the state value function, which, if you remember, is just a function of the state. And there's a lot of theoretical work that shows that once we do that, we get much better convergence guarantees, we reduce variance, and we get a better overall algorithm. So actor-critic algorithm, the overall architecture is a mix of value learning, which we use as the baseline, which comes from the TD error, and this reinforced style policy learning, which uses the TD error essentially for the gradient of the policy. You can see that here, basically what I just explained, like reinforced with baseline, and actor-critic method just replaces in the value estimate, and then we can also do the TD learning as well, or like even n-step returns to approximate the return at the current state, and this is in essence what actor-critic methods are. And you will see that in the tutorial later on. So yeah, I mean, you might have seen A2C, A3C. The difference between the two is just 1A is asynchronous, so A3C is a bit more parallelizable, but essentially it does what I mentioned. We compute the return, the full Monte Carlo return usually, but you can also do n-step returns. We compute the advantage, which is this unbiased return, and then just apply the method on its own and optimize via Adam. And in a lot of cases, we've seen that this outperforms DQN. And as I mentioned before, like Q-learning is generally often less sample efficient than the policy, than these kinds of methods. To introduce another family of policy gradient methods, we can look at sort of the intuition around a surrogate objective. So when we think about what policy optimization does, if we're doing it, say, in an on-policy setup, we have a policy which is used to generate some data, and now we want to make an update based on that. So we want to use the data from sort of what we call an old policy and use those data to now make an update. And we can use a trick like this where we can rewrite the objective using the importance sampling where we just compute the expectation over the old policy, so the policy that the data was generated by, but now do the reweighting of like this is the importance weighing coefficient here, 1 over pi old. And we use the trajectories generated, as I mentioned, from pi old. And then we can do the policy gradient here. And this essentially gives rise to two important methods that are widely used. First one is called trust region policy optimization. So here we use this rewritten policy objective, but then we also want to, for robustness, we want to specify the maximum distance between these policies and limit that. So we don't want to make too big of steps once we make the update. So this is what this KL term here does. KL is just a measure of how different two distributions are, and we want to keep that less than a specified boundary. So we want to improve, but we don't want to make too big of a changes to destabilize learning. And TRPO has also shown tremendous improvement in stability and speed of learning. And then something that you might have been are familiar with from the RLHF literature is PPO, which got popularized within RLHF. And PPO is just a way of rewriting the constrained optimization that we have in TRPO, where we have an explicit constraint here, but you can use Lagrange multipliers procedure to turn the constrained formulation into an unconstrained formulation, where we have the Lagrange multiplier beta, and then plus a few more tricks to stabilize learning, we got like a really nice and simple algorithm called PPO, which is very widely used, especially in RLHF nowadays. And this has been applied to various domains, from locomotion, Atari games, and so on. This slide I'm going to skip because this algorithm is not super widely used and it gave me a lot of headache in the past, so no. So this was it on the policy-based methods, so methods where we directly aim to learn the policy, or we get the best of both worlds, which we generally do by like learning both the policy and value to reduce variance. This is an application level choice. So similar to other things that we mentioned, other hyperparameters, this is also like an algorithmic choice that that are task specific. It depends actually on, it really depends on the problem at hand. So one example that I took from one of Peter Abil's classes is this example of catching a rugby ball. So if someone throws a ball and you want to catch it, a value-based approach would be to try to predict how the rugby ball would move, what's your probability of catching it, and to estimate the probability of catching the ball, you really actually need to implicitly learn about the whole dynamics and physics around the ball flying and all that. But instead, what you can do is you can just think of it as a policy optimization where you just look at the ball and you try to run towards the ball as it's flying and hopefully catch it. So in this case, policy is much simpler, and learning a policy can be way simpler than learning everything that constitutes a value that would allow you to predict how likely you are at catching the ball and then slowly iterating on that. And there's many other different use cases where you might want to prefer one over the other. So to wrap up, there are a lot of open questions in RL still, and there is this huge gap between theory and practice. So as we've seen, things are very well understood in the grid world domains, but as soon as we start adding function approximation, we start adding different biases, and we start having to need different tricks to stabilize numerics and learning and so on, and we get into these semi-gradients and all that stuff. So there's still a lot of work that could be done to align those. There's also a lot of work to use different environment models for planning, such as the continuation of AlphaGo, mu0, and so on. These things we haven't covered today, but they're very important and are now also a lot of people consider those the key next steps for language modeling research as well. And then, as I mentioned, exploration is still very much an unsolved problem. Finding interesting parts of the state space to visit, covering the space especially for large unstructured states, is a very difficult task, and there's a lot to do there. To summarize, we've talked about the main components of an RL agent, the policy and value networks, which help us train agents to perform well on maximizing the reward at specific tasks. We talked about episodic versus continuing RL tasks and how the choice of reward is important, and how it might need to be adapted based on the task at hand. We talked about the value functions, the problems that come, how we can estimate them using Monte Carlo or TD learning, and the problems that come with function approximation, but also the benefits that we get from that. We contrasted Monte Carlo, TD learning, talked about the bias and variance that those introduce. We talked about the Markov property and how that connects with TD learning and dynamic programming. We mentioned on-policy and off-policy control methods, depending on whether we're optimizing the policy that we're currently executing versus we just have some data, some transitions, or like are optimizing a policy that we're not executing. So for example, we choose the maximum action to bootstrap versus the action that we've taken. And we've also mentioned this exploration versus exploitation, which is an open problem, and in grid world, we do have some convergence guarantees and results, but still in like unstructured state spaces, not so much. So this is the last slide. I'm open to take some questions. So the question is about transfer learning in reinforcement learning. So essentially, how much, what we can do in terms of transfer learning between different environments and different tasks, and potentially even, I guess, going from simulation to real-world problems. So yeah, we haven't touched that in this presentation, but it's an ongoing line of work, and there's a lot of interesting things there, especially I guess on this kind of sim to real, like moving domains, where we want to transfer an agent that's trained in an environment in a closed world and bring it into the real world. So it's a whole research topic on its own. I think it depends heavily on like how similar environments are, but it is essentially, and it has been an important task in reinforcement learning from its inception, because from its inception we've been thinking about these generalist agents that can work across many different environments. And with the hope of then having those agents be able to generalize when we put them into a new environment that let them perform well. And we do see that. We do see that, like, as we give agents more signal across different environments, like those agents become better across the board and are able to generalize and transfer and so on. So yeah, it's a very interesting direction, but yeah, I don't know. You're going to give a full talk about that. Okay, cool.